In analyzing heat conduction through multi-layer solids, we assumed perfect contact at the interface of two layers and thus no temperature dropped at the interface. This would be the case when the surfaces are perfectly smooth and produce a perfect contact at each point. In reality, however, even flat surfaces that appear smooth to the eye turn out to be rather rough when examined under a microscope. Air interface contains numerous air gaps of varying sizes that act as insulation because of the low thermal conductivity of air. Thus, an interface offers some resistance to heat transfer, and this resistance for a unified interface area is called the thermal contact resistance, denoted as R subscript C. The value of Rc is determined experimentally using a setup like in the illustration. Consider heat transfer through two metal rods of cross-sectional area A pressed against each other. Heat transfer through the interface of these two rods is the sum of the heat transfers through the solid contact spots. The gaps in the non-contact areas, which is a significant contributor to heat transfer, can be expressed as illustrated. It can also be expressed analogously to Newton's law of cooling, presented in equation 326. A is the apparent interface area. Delta T interface is the effective temperature difference at the interface. The quantity H subscript C is the convection heat transfer coefficient called the thermal contact conductance and is expressed in equation 328. The thermal contact resistance can be minimized by applying a thermally conducting liquid called a thermal grease, such as silicone oil, on the surfaces before they are pressed against each other. This is commonly done when attaching electronic components such as power transistors to heat sinks. The thermal contact resistance can also be reduced by replacing the air at the interface with a better conducting gas such as helium or hydrogen, as shown in Table 3.1. Table 3.2 shows some experimental results for the contact conductance between similar and dissimilar metal surfaces for use in preliminary design calculations. Note that the thermal contact conductance is highest for soft metals with smooth surfaces at high pressure. The thermal resistance concept or the electrical analogy can also solve steady heat transfer problems involving parallel layers or combined series parallel arrangements. Although such problems are often 2 or 3-dimensional, approximate solutions can be obtained by assuming one-dimensional heat transfer and using the thermal resistance network. Consider the composite wall, which consists of two parallel layers. The thermal resistance network, which consists of two parallel resistances, can be represented as shown in the figure. The total heat transfer is the sum of the heat transfers through each layer as shown in equation 329. Utilizing electrical analogy, we get equation 330. R total is expressed in equation 331 since the resistances are in parallel. Now consider the combined series parallel arrangement shown in the following figure. The total heat transfer rate through this composite system can be expressed in equation 332. R total is described by equation 333. Once the individual thermal resistances are evaluated, the total resistance and heat transfer rate can easily be determined. The result obtained is somewhat approximate since the surfaces of the third layer are probably not isothermal, and heat transfer between the first two layers is likely to occur. Two assumptions are commonly used in solving complex multidimensional heat transfer problems by treating them as one-dimensional using the thermal resistance network are: any plane wall normal to the x-axis is isothermal, and any plane parallel to the x-axis is adiabatic.